Hey everybody, it's Elliot here, and this is my video tutorial on metabolism, glycolysis, and matrix reactions. Now, there's lots of images about glycolysis and matrix reactions, and ETS for that matter, on the internet that show full structures. And I just decided that I wanted to do my own graphics and my own sort of style to do this. So by all means, check out some of those other graphics and follow along with mine and see how they compare or whatever. There's going to be a few differences, I'm sure, but in general, what we've got here, let's just get the pen out here. What we've got is a cell here. So the cell membrane is right out here, right? And of course, glucose is going to have to enter the cell through the phospholipid bilayer, and it can do that through facilitated diffusion, through a channel, through some kind of carrier-mediated facilitated diffusion, or through an active transport pumping mechanism. And it's going to go through glycolysis, and then we're going to enter the mitochondrion. That's this structure here. This is the mitochondrion. And in the matrix of the mitochondrion, we're going to have the matrix reactions. And from there, we're going to move over to the ETS, and that's going to take place here on the cristae. And I've just put some yellow blobs to indicate that that's where the electron transport system would occur. So we start off with glycolysis here, and the glycolysis is going to produce some ATP, not very much, but a little bit of ATP, 2 ATP. ATP, of course, is adenosine triphosphate. It is the energy-carrying molecule, or the energy-storing molecule. That's the whole purpose for all of this cellular respiration stuff. And it's going to produce some NADH. Now, the NADH is going to be used later on in the ETS to create a whole bunch of ATP. And glycolysis is also going to produce a couple of pyruvate molecules. We'll have a look at those in a moment. The pyruvate is then going to enter the mitochondrion and go into the matrix and go into the matrix reactions. And that will include pyruvate oxidation, so it'll be oxidized, and Krebs cycle itself. So we'll have a look at both of those structures, reactions. Matrix reactions is aerobic, although it only requires oxygen. That's what that means, in an indirect way, whereas glycolysis is anaerobic out here in the cytoplasm. It's not going to require any oxygen. Matrix reactions will, but you'll see how later on. Matrix reactions will lead to the production of 2 ATP, 8 NADH. These are electron carrier molecules that are going to be used in the ETS, and FADH2, which is also an electron carrier used in the ETS. So that's what the matrix reactions will produce. That's what glycolysis will produce. And then we'll come over to the ETS, and though I'm not going to cover that in this tutorial, the ETS will produce a lot of ATP, 32 or 34 ATP, depending on which type of tissue it's in. And we'll discuss that at another time. And it is definitely aerobic. Oxygen is definitely needed here. All right, so that's just a little summary of where we're going with this. So let's have a look at the first bunch of reactions. Now, this is my interpretation of glycolysis here. All right, so we're going to be starting over here with glucose, and we're going to go through this pathway, and we're going to end up with the molecule of pyruvate, like we said before. So if we start up here with glucose, we can see that glucose is a 6-carbon molecule. All right, it's got 6 carbons starting here, 1, 2, 3, 4, 5, and then the 6th one is up in there. It's got some oxygen, some hydrogen here, but not all of the molecule is drawn, so don't worry about keeping track of all of the atoms. The important atoms to keep track of are the carbons and what's going on up here. So glucose is going to be converted by an enzyme that would be right here at this arrow, and we're not going to worry about the names of the enzyme. All right, glucose would be converted to a molecule here. Now, I'm giving the abbreviations. It's hard to fit all of them on these egg-like structures, but this stands for glucose 6-phosphate, and that's because a phosphate group is added to the 6th carbon. So there's the 6th carbon, and this P represents a phosphate group. In order to gain that phosphate group, it has to come from somewhere, and it comes from a molecule of ATP. Now, ATP, adenosine triphosphate, has 3 phosphate groups. And again, this is occurring in the cytoplasm. And ATP will interact with glucose. Imagine it collides with glucose, donating a phosphate group. So it phosphorylates the glucose, adds the phosphate group there. And then the ATP is now converted into ADP, adenosine diphosphate. It's lost its phosphate group. So we now have a molecule of glucose 6-phosphate. This molecule will be converted to fructose 6-phosphate, which is an isomer of glucose. And you can see the phosphate over here and a different structure for fructose 6-phosphate. We still have our 6 carbons though, so that hasn't changed. Fructose 6-phosphate will be converted into this molecule. So this is a biochemical pathway or a metabolic pathway. Each arrow represents an enzyme or enzymes, and this is therefore the substrate for an enzyme, and this is the product. All right, so an enzyme will take this substrate, convert it to this product. So for fructose 6-phosphate to be converted to fructose 1,6-bisphosphate, that's what the abbreviation stands for. Bisphosphate means 2 phosphates, and they're on carbon 1 and carbon 6. And you can see a P there and a P there. Now we had this one here from before, from over there. So we're adding a new phosphate group over here, all right? And that phosphate group has to come from somewhere, and it comes from another ATP. So we're using ATP in these first early steps of glycolysis. This is energy requiring. We use some ATP, phosphorylate the molecule, releasing ADP. So this is the second ATP we use, the second ADP we produced. And now this molecule has 2 phosphates, fructose 1,6-bisphosphate. Now, this is a big molecule, and at this point, fructose 1,6-bisphosphate is going to get cut. So imagine it comes down here and it gets cut into 2 pieces. We're going to get this one and we're going to get this one. That's why I have these 2 arrows. So fructose 1,6-bisphosphate is cut into 2 molecules, DHAP, dihydroxyacetone phosphate. So we still have a phosphate on there. And G3P, glyceraldehyde 3-phosphate, so we still have a phosphate there. Now, it's, it's just inherent in the name, glyceraldehyde, so we've got a glycerol backbone, and we've got an aldehyde functional group right there. So that's glyceraldehyde 3-phosphate, and dihydroxy, all right, so there's a hydroxy there. Actually, I'm not going to explain that very well, so forget it. Acetone implies there's a ketone part. There's the ketone. I don't know how well you can see the double bond. Phosphate. All right? Those are the 2 molecules that are produced when fructose 1,6-bisphosphate is split. But the glycolysis pathway can only work with glyceraldehyde 3-phosphate. And so even though this is produced, it's quickly converted to another one of these. So at this point, there are really 2 glyceraldehyde 3-phosphates. So therefore, there's 2 times this, and then the rest of the pathway is going to occur twice as this stuff gets converted into this stuff. So we would no longer have this. We've got 2 of these, but I mean, I didn't do this twice. I'm just showing the pathway continuing once. All right, assume that you're with me so far. Glyceraldehyde 3-phosphate. This molecule is going to gain a phosphate that's floating in the cytoplasm. This is an inorganic phosphate. All right, it's not attached to an organic molecule. This will click on so that there will be 2 phosphate groups. And as you can see, the product will have 2 phosphates. So we gain a phosphate to convert to this. But there's another part of the reaction. NAD+. Now, NAD+ is an electron carrier molecule. And NAD+ will gain electrons and hydrogen and be converted to NADH. So let's have a look at my little scratch pad here, and we will take a couple of notes here. So we are going to go from NAD+, and we are going to convert this to NADH. Now, when that happens, this reaction is a reduction. NAD+ is being reduced and converted into NADH. In order for this to happen, this molecule has to have interacted with another molecule, all right? And that is an oxidation of the other molecule. All right, so NAD plus comes along, oxidizes a molecule, picks up electrons and hydrogen, and is converted to NADH. That's a reduction. So the oxidation and reduction reactions occur together. So let's have a look at that. NAD plus floating in the cytoplasm, just imagine a big molecule, bumps into G3P, grabs electrons and hydrogen, and is now converted into NADH. Now, I just drew the electrons here, not that they're sort of, separate from the molecule. They're part of the molecule, but just so that you can see it's got the electrons, because we're going to use this stuff later. This stuff will go out of the cytoplasm into the mitochondrion for use in the electron transport system, which we'll pick up later. Both of these reactions produce a molecule of 1,3-bisphosphoglycerate. All right, like this bisphosphate, bisphosphoglycerate. It's still got the glycerol backbone, that's why it's glycerate, and it's got 2 phosphates, that's why it's bis. Now we are ready to produce some ATP, finally. 1,3-bisphosphoglycerate is a substrate for the enzyme here that will convert this substrate into the product 3-PG, or 3-phosphoglycerate, with just 1 phosphate. One of the phosphates is being lost, and it's going on to ADP. So when ADP is phosphorylated by this molecule, it becomes ATP. Now, an important term for you guys to know is substrate, that's an E, level phosphorylation. These lines are not helping me draw straight, are they? Substrate level phosphorylation. Bang. What this means, substrate level phosphorylation, means a phosphate group comes from a substrate in the pathway. Get out of there. Boom. All right. What I'm saying is the phosphate group here is going on to ADP to make ATP. Because this molecule that is giving the phosphate to ADP is a substrate in the pathway, this is called substrate level phosphorylation. All right. There's another one coming up over here. Now, this is going to be important to distinguish from oxidative phosphorylation, which happens in the mitochondrion, and we'll see that later. So, in a substrate level phosphorylation, 1,3-BPG gives a phosphate group to ADP, producing our first ATP. But remember, this is happening 2 times, all right? Go and check out some other textbooks for images of this, and you'll see it's happening twice. So there are 2 ATP that are going to be produced at this point. We are left with the molecule of 3-PG, 3-phosphoglycerate. This is converted to 2-phosphoglycerate. You can see the phosphate group here has moved to the middle carbon here, the two carbon. Number 2 carbon, all right? Water is removed, H2O. That leaves us with the molecule of PEP, PEP, phosphoenol pyruvate. In a final substrate level phosphorylation, PEP phosphorylates ADP to produce our high energy molecule of ATP, all right? Leaving pyruvate as the final product in the glycolysis pathway. You have to remember, however, that this happened 2 times, all right? Because we had this one coming to this, so we really had 2 eggs there. So there are 2 ATP made, 2 waters, we don't care about that, and 2 more ATP there. We used up 1 ATP there. We used up 1 ATP there. Okay, so these ATP are gone. That ATP was used up. So although we made 4, we use 2, so our net ATP is 2 ATP. Okay, that's important. We make 2 ATP. We also make 1, where's the other one? Well, it's times 2. I'm forgetting myself. 2 times these, so we have a net of 2 NADHs as well. All right, those will be used in the ETS. And we have our final 2 pyruvates. Those molecules are now going to enter the mitochondrion. So let's go on. Now in this image, similar to the first one, we have our cell membrane out here, we have our mitochondrion right here, and here's the pyruvate. This pyruvate started as glucose here, went through glycolysis, which split. There are really two pyruvate molecules. I'm just following one, right? There are two pyruvates. Note that each pyruvate has 3 carbons. So if this is a pyruvate here and there was another pyruvate down here with 3 carbons, we have the original 6 carbons. That's a 6 and that's a G. Funny looking G. We have the 6 carbons that we originally had in glucose. We now have 3 carbon molecules of pyruvate. Pyruvate will be converted to acetyl-CoA in this reaction, which is pyruvate oxidation. So pyruvate is going to be oxidized into acetyl-CoA. Now, what's an oxidation? Well, one of the definitions is loss of electrons and hydrogen. So along comes NAD+ inside the matrix of the mitochondrion, so that this is part of the matrix reactions. Remember, the matrix reactions is 2 things: pyruvate oxidation and Krebs cycle. So here's the first part, pyruvate oxidation. Pyruvate and NAD+ interact. NAD+ takes electrons and hydrogen, producing NADH with its electrons. That has oxidized pyruvate. NAD+ is being reduced to NADH. Pyruvate is being oxidized to acetyl-CoA. Now, to make it acetyl-CoA, there's a molecule called CoA here, coenzyme A, and here it is being added. So this one goes on, so that's where you get the CoA part from. By the way, a carbon dioxide comes off. Now, this is our first CO2 released in cellular respiration, and this is the CO2 that you exhale, part of it, right? So glucose will be converted to CO2 and other things, but we are finally losing one of the carbons. So if we had 3 carbons here and we have 2 carbons here, one of the carbons has been lost as CO2. All right. We now have acetyl-CoA, and we've done the first part of the matrix reactions. We've done the pyruvate oxidation. We are now going to do the big circular biochemical pathway called Krebs cycle. So let's have a look at that. So we're starting with acetyl-CoA, which will go into Krebs cycle. And so here it is. Here is the acetyl-CoA. Let me actually just draw here. There's the acetyl-CoA. And we had our pyruvate over here, and we converted it into acetyl-CoA. Now, pyruvate had 3 carbons. Notice acetyl-CoA has 2 carbons. All right. Now, acetyl-CoA will react with this molecule. So this is a cycle here. This is called Krebs cycle, but acetyl-CoA comes into the cycle, whereas this is already there, so they come together like that. All right. This molecule is called oxaloacetate. Now, you're not going to worry about the complicated structure. And I want to remind you, by the way, if I haven't said this, that in terms of the structures I've drawn here, the most important things to keep count of are the carbons. Some of the hydrogens will fluctuate a little bit, and you won't be able to account for them all the time because there's a little bit more going on in these reactions than is drawn here. All right. And that even shows up in typical sort of grade 12 textbooks. There's more to it, so don't worry about that. Just concentrate on the carbons. So acetyl-CoA, which looks roughly like this, will lose the CoA group with some sulfur and hydrogen, so CoA-SH will come off. So just imagine this brown thing comes off, and you're not going to see it in this molecule here in the product. But acetyl-CoA with its 2 carbons will bind with oxaloacetate, which has 4 carbons. So let's keep track of the carbons. 4 carbon molecule here, 2 carbon molecule here gives us 6 carbons. All right. This molecule is called citrate or citric acid. And the Krebs cycle is sometimes called the citric acid cycle. All right. Because the first organic molecule that includes the acetyl-CoA from your food, because it originally came from glucose that you ate, the first organic molecule has 6 carbons and is citrate. And we are now ready, and we're in the pathway. So imagine this is a car merging onto the highway, and now you're in, all right? Although your car's changed to a citrate car, whatever. Okay, so citrate is going to be converted into an isomer called isocitrate. So there's going to be an enzyme here that does that. Nothing big to worry about. These are some pretty big reactions here, though. A lot of stuff's going on. So let's look at this. Isocitrate has 6 carbons. It's going to lose another carbon dioxide molecule here so that the product here, count the carbons, has 5 carbons. So we can keep track of that. So we go from 6 carbons to 5, losing a carbon dioxide. Think of this carbon dioxide came from the original glucose, which was converted to pyruvate, which was converted to acetyl-CoA, into citrate, and now you are breaking off the carbon that originally came from your food. We had lost one up here in the pyruvate oxidation. We've lost another one here. So this carbon dioxide that you are breathing out came from the glucose that you ate. In addition to this decarboxylation, this removal of carbon dioxide, isocitrate is oxidized by NAD+. That means NAD+ takes electrons and hydrogen away from it. So isocitrate is oxidized. This reduces NAD+ to NADH. We're making more of that stuff. We made some in glycolysis. We made some in the pyruvate oxidation. So we need this stuff for the ETS later on. That converts the isocitrate into this molecule, alpha-ketoglutarate. We are down to 5 carbons. Another decarboxylation occurs. Another CO2 is removed. All right, that'll take us from 5 carbons down to 4, and another oxidation reduction reaction occurs. Alpha-ketoglutarate is oxidized, converting it to succinyl-CoA. We've made some more NADH, which we're going to need. Now we have succinyl-CoA, but wait, where did the CoA part come from? We didn't have it here. Well, a molecule of CoA with SH comes onto here, clicks on, and now we have it there. All right, this is called succinyl-CoA. In the next step, to convert succinyl-CoA into succinate, the CoA-SH will just come off. So it came on, came off. It's like taking a bus, going for one stop, being dropped off. There is a complicated reaction down here that I've simplified to show the production of ATP. There's another high-energy molecule called GTP, but I'm not going to worry about it for this video. So ATP is produced from this molecule. But the weird thing that you might ask is, where is the phosphate group? And you often will not see a phosphate group added and then phosphorylated onto ADP. You just have to take my word for it that somehow there's enough energy here to produce ATP. This is substrate level phosphorylation again, because the substrate, the phosphate will have come from the substrate. And I wish I could show you that here, but I can't. But the phosphate will have come from here onto ADP. So this is a substrate level phosphorylation and the production of ATP. Now I want to say something about this. Although we see one ATP produced here, we see one NADH, we see one NADH and all of that, we see one acetyl-CoA. I want you to remember that glucose was converted into 2 pyruvates. Each pyruvate was converted to an acetyl-CoA, would go through the cycle. Here's another one going through the cycle. So really, this is all happening twice. All right? So it happens twice per glucose, once per pyruvate, or acetyl-CoA, twice per glucose. So really, the net result for glucose is going to be twice the amount that we see here. Okay, let's go on. So we are down at succinate. We have produced our high-energy electron carriers, which we'll need later. And there's another high-energy electron carrier called FAD. Similar to NAD+, FAD picks up electrons and hydrogen from a substrate in the pathway, in this case succinate, and when it picks up electrons and hydrogen, it's converted to FADH2. We are not worrying about a quantitative look at exactly how many hydrogens and electrons. We just are thinking of these as taxis. People, electrons and hydrogen are getting in, and they're going to be deposited somewhere, and that's all we care about. In doing this reaction, fumarate is produced. All right, so succinate reduces FAD. See, I said that a different way. I didn't say FAD oxidized succinate. I said succinate reduces FAD to produce FADH2. That leaves us with a molecule of fumarate. What do you do when something's fuming or on fire? You add water. So water is added to fumarate, and that converts it to a molecule of malate. Now, we haven't lost any carbon for a while, since back here we had 4 carbons, 4 carbons, 4 carbons, 4 carbons. We're going to our last step. Malate will be converted back to oxaloacetate when NAD plus is converted to NADH. So malate reduces the NAD plus, gives it electrons and hydrogen, making some more of this stuff, and that brings us back to oxaloacetate. This molecule, oxaloacetate, is our acceptor molecule for acetyl-CoA. It's a 4-carbon molecule, and as you can see down here, we had 4 carbons. Whoops, carbons, not... 4 carbons, 4 carbons, 4 carbons, still 4 carbons, still 4 carbons. Don't forget 2 carbons coming together to make 6 carbons. 6 carbons, we lose 1. 5 carbons, we lose 1 down to 4. All right. This molecule here was a very important one because it was our acceptor molecule for acetyl-CoA. So think of it as you eat your food, you break it down eventually into acetyl-CoA units, 2 carbon subunits, and then you bring this in with oxaloacetate, and then you go around the cycle. Now, you've added 2 carbons to the cycle, right? I mean, this stuff exists as it is in the matrix of the mitochondrion, okay? So if this is the mitochondrion, actually, I'll use that as the matrix. There's the outer membrane of the mitochondrion. This is happening right in here in the matrix. These molecules exist naturally. You're bringing in a new one. These are the cars on the highway. You're merging onto the highway with a 2-seater car, right? A 2-carbon car into here. But look at this. You spit out 1 carbon there. You spit out 1 carbon there. So the 2 carbons that you brought into the cycle have been lost right there, and nothing else has really changed. You made some stuff and all of that. All right. So the other thing to remember, if you want to keep track of all the carbons, is we lose 2 carbons in this 1 Krebs cycle turnaround, right? But I also said that this is happening twice. There are 2 pyruvates being converted to 2 acetyl-CoAs. All right, so this happens twice. That means you are losing 2 carbons here. 2 carbons. That's a total of 4 carbons. Well, the other carbons were lost. I'm just going to go back for a second. Right here. We see a CO2 coming off. That's 1 carbon right there. But remember, there are 2 pyruvates. So that gives us 2 carbons. So the 2 carbons here, and then in Krebs cycle, went around something like this, right? We lost 2 carbons from CO2 there, 2 CO2s, 2 CO2s there. Of course, meaning this cycle really is happening twice. You know what? I probably shouldn't have done it like that. Let me do it a different way. Let me do it this different way. 1 carbon there, but this is happening twice. All right, so we're going to lose another one when we have the other reaction. And for Krebs cycle, 1 carbon there, 1 carbon there, okay? But this happens twice. We lose a CO2 and another CO2, and look at what we have, 4, 5, 6. Well, C6H12O6, there's our glucose. This accounts for the carbons of glucose. So by the time we get through the matrix reactions and then, the matrix reactions and then Krebs cycle, or really the pyruvate oxidation and Krebs cycle here, we have broken down our original glucose all the way into what's left here. We've gotten rid of all the carbons. We've stored some high energy electrons in the NADH. Those high energy electrons are going to go over to the ETS. We've got some NADH over here. We've got some NADH over here. We also have some FADH2. These are going to feed in to the electron transport system, the cristae, or the folds or bumps of the mitochondrion. So those electrons are going to go into the electron transport system and generate quite a bit of ATP. We're going to have to see how this stuff is used here, because in order to get the electrons to the ETS, something special has to happen. And there's some issues with this, but we'll talk about that later. All right. So that's my summary of metabolism, glycolysis, matrix reactions. Hope it helps. Good luck. See you later.